Right. So in the previous sections, we assume that K value is constant. So this assumption is good for smaller temperature variation. But when the temperature difference is large, then K value significantly varies with temperature. Okay. Most of the engineering materials, as I mentioned previously also, are homogeneous and isotropic. So most of the engineering materials are homogeneous and isotropic. And for isotropic material, we can write like K as a function of temperature. Okay, so for homogeneous and isotropic material, K or thermal conductivity varies linearly with temperature, and we can write like this: plus minus beta T. Plus or minus depend on the material itself. Okay, so K naught is a constant, right? Or it is a thermal conductivity value at 0 degree Celsius. It is a positive constant. Right, and beta is the temperature coefficient of thermal conductivity, right? And beta measure the effect of temperature on K value, right? If beta is positive, then thermal conductivity will increase with the increase of temperature, and if beta is negative, the thermal conductivity will decrease with increase of temperature. Okay, and if beta is 0, then thermal conductivity is constant, no variation. Okay, so let me put that in words. If beta is 0, K is constant. And if beta is positive, for non-metals and gases, for that case, thermal conductivity increases as we increase the temperature. And if beta is negative, in this cases generally occur with metals and liquids. And for this case, thermal conductivity will decrease as we increase the temperature. Okay, but let's say this is the temperature, this is the thermal conductivity variation with temperature. Okay, but we need a mean value. We need a mean value of this thermal conductivity in this particular range. Right, for calculation purpose. So how can we find? By dividing this area with the temperature difference, T1 minus T2 minus T1, right? So let me write. In general, we can write K average as integration of, we take a small strip of this rectangle, small rectangle, having this thickness dt and height as K, and K is variation with temperature, and dividing this by T2 minus T1, and this limit is from T1 to T2. So this is depicting the area and this is depicting the temperature difference. So that's how we can find the average value of thermal conductivity. So if we plug in this here, we can find the average value. So let's find this. K naught is constant, so it will come out of integration. So 1 plus minus beta t dt integration from t1 to t2, okay, divided by t2 minus t1 . So if you solve it, the average value will come out to be 1 plus minus beta t1 plus t2 by 2, right? So that is, so if we write t1 plus t2 by 2 as t average, so if the thermoconductivity variation is linear with respect to temperature, then average value will be k naught times 1 plus beta 1 plus minus beta times t average, right? So after knowing this average value of thermoconductivity, we have to find the temperature variation inside the body, right?